Transformers power ChatGPT, Claude, Gemini, and almost every serious language model today. But the core idea is not magic. It is a repeated block that does two things. Tokens exchange information, then each token computes an update. That is the pattern. Communication, then computation. Repeat it many times, and token vectors become a prediction about what comes next. In this video, we will follow one sentence through one transformer block. Tokens, embeddings, attention, the MLP, and the final next token prediction. Start with a sentence. The dog chased the ball because it bounced. A language model does not see that as letters or words. The tokenizer converts text into token IDs. Those IDs index into an embedding table, so every token becomes a vector, a list of numbers the model can update. But vectors also need position. If you shuffle the tokens, attention does not automatically know the original order. So the model adds position information. The original transformer used sinusoidal positional encoding. Many modern LLMs use rotary position embeddings, a newer way to encode position. The important idea is simple. Each token enters the block as a vector that represents what the token is and where it appears. Inside attention, every token creates three new vectors: a query, a key, and a value. The query means, what am I looking for? The key means, what information do I advertise? The value means, what content do I carry forward? The word "it" is a good example. In our sentence, it is looking for the thing it refers to. The keys for dog and ball both compete as possible matches. The value vectors contain the information that would be copied forward if a match is strong. These are learned projections, not handwritten rules. During training, the model learns what questions are useful, what keys should match, and what information should flow through values. Now every query is compared with every key. This creates an attention score matrix, token by token, row by row. For it, the model asks, how well does my query match each key? Maybe ball gets a high score. Maybe dog gets a lower score. Filler words get almost none. This is the first big insight. Attention is a full grid of relationships. Every token can look at every other token in one parallel operation. That is why transformers replaced recurrent networks. A recurrent model passed information step by step. A transformer creates direct connections between positions, even when they are far apart. Raw scores are not the final output. First, they are scaled, then passed through Softmax. Softmax turns each row into a probability distribution. A token might assign 70% of its attention to ball, 15% to dog, and small amounts to the rest of the sentence. Then those probabilities mix the value vectors. High attention tokens contribute more, low attention tokens contribute less. So the output for it becomes a new vector that still represents it, but now carries context from ball. The token has absorbed information from the sentence. That is self-attention. Compare, normalize, blend. One attention pattern is useful, but language has many relationship types at once. A token may need reference, grammar, position, phrase, structure, and topic information. One attention head is one lens. Multi-head attention gives the model several lenses in parallel. One head might track what it refers to. Another might focus on nearby words. Another might follow subject-verb structure. Another might watch punctuation or phrase boundaries. Each head has its own learned query, key, and value projections. Each produces a context vector. Then those outputs are joined and projected back to the model's normal vector size. After attention, tokens have exchanged information. Then comes the feed-forward network, often called the MLP. This step is applied to each token independently. No token talks to another token here. Each token processes the information it already gathered. A clean way to remember the block is, attention is communication. The MLP is computation. In the original transformer, the MLP expands the vector to a larger hidden dimension, applies a nonlinearity, then projects it back down. Modern models often use gated activation functions, but the role is the same: transform features and build more abstract representations. A real transformer block also includes residual connections and normalization. The residual connection is the skip path. Instead of replacing the token vector completely, the block adds an update to the existing signal. That gives information and gradients a clean route through the stack. Layer normalization keeps vector values stable. Without it, repeated updates can drift or become hard to optimize. So the pattern is: normalize, run attention, add the result back. Normalize, run the MLP, add the result back. Then the next block repeats the same structure. One block adds a little context. Dozens of blocks gradually build richer representations: syntax, references, facts, relationships, and task behavior. After the final transformer block, each position has a context-rich vector. For a causal language model, the vector at the last position predicts the next token. That vector is projected into the vocabulary. If the vocabulary has 100,000 tokens, the model produces 100,000 scores. Softmax turns those scores into probabilities. During training, the model compares its prediction to the real next token and updates the learned matrices through backpropagation. During inference, we choose or sample a token, append it, and run the process again. That loop is how an LLM writes: predict one token, append it, predict the next one. So the mental model is this: tokens become vectors. Attention lets them exchange information. Multi-head attention gives several views of context. The MLP computes new features. Residuals and normalization keep the stack trainable. And the final vector becomes a probability distribution over the next token. That is the engine inside modern language models. The details vary: rotary embeddings, gated MLPs, grouped query attention, mixture of experts, larger context windows, but the core pattern remains: communication, computation, repetition, prediction. If the tokenization video showed how text enters the model, this is what happens next.